In this video lecture, we're going to discuss the rules of exponents. We're not going to discuss them just at the surface level. We're going to dive deep into why the rules make sense. The goal is for you to not just memorize these rules, because memory, you can memorize something for a test, for an exam. You will remember it for a few days, and a few days after that, you have already forgotten it. The goal is for us to understand the things in such a way that it just makes sense like a story, where you can feel it inside your bones that yes, it does make sense. You know what I mean. Those who are new on this channel, this lecture, it is lecture number 2 on rules of exponents. This playlist, it is called Algebra Readiness series. Here in this series, on this playlist, what I'm doing is that I'm going over several topics of pre-algebra for you to assess if you're ready for algebra, or maybe you are a pre-algebra student. This series is going to be super helpful for you to enhance your understanding of topics of pre-algebra. Or maybe you are a grown-up who's rusty on their pre-algebra skills and wants to just brush up on their skills. So this series is for you. What I'm doing here is this. Each topic is divided into 3 lectures. The first lecture, I'm calling that as a pre-test. In that pre-test, what we're doing is I'm presenting you with a series of problems on that topic. And I'm giving you enough time to either take a screenshot or just pause the video to solve that problem and write down its answer. Then you move on to the next problem and the next problem and so on. After we have finished all the problems, then we are going to go over the answers. Now mind it, I did not say solutions, I said only answers. Then you're going to score this pre-test based on the answers that I'm providing you. This pre-test is going to help you assess how much you understand that topic. Maybe you have scored 100%, or maybe you did not score 100% due to silly mistakes. Then I say that you're good. You do not need to move on to the second lecture for that topic. But if you did not do so well on your pre-test, then I highly recommend that you move on to the second lecture for that topic. In that second lecture, which this lecture is for exponents, we are going to go over that concept in detail. And hopefully by the end of that lecture, you have completely understood that topic. Please let me know in the comments how helpful these lectures are for you. I am more than willing to modulate my teaching style to match your learning style. Alright, back to the discussion of structure of these lectures. At the end of the discussion of lecture number 2, I will present you some problems on that topic again. And I want you to solve those problems and write down your answers. Let's call these questions as your post-test. After you have taken the test, then I will present you with the answers. And I want you to score your post-test. Hopefully you have all scored 100% by now. But for if whatever reason, there is a question or two that you didn't quite understand how to solve, then there is going to be a lecture number 3 in the series for that topic, where I'm going to solve all the problems that I assigned to you at the end of lecture number 2. So here you go. This is the entire structure of these lectures. The Algebra Readiness series is basically pre-algebra, where I'm going to go over several topics of pre-algebra that if you don't know, you absolutely cannot excel in algebra. And each of these topics, it is organized in 3 lectures. The first one, pre-test, where you assess yourself. Second one, lecture number 2, is the discussion of that topic, followed by a post-test. Lecture number 3, solutions for post-test. Make sense? I hope it does. I am Dr. Rima McMullen, and here at ACEM Academy, my goal is to spread my passion and love of mathematics, physics, chemistry, and science in general with you all. Alright, with the introduction being out of the way, let's now begin with our lecture number 2. I want to open this lecture with a question for you guys. How many of you have never seen a power expression? What is a power expression? Well, this is a power expression. I'm hoping to get no positive answer. In other words, I'm hoping to get a negative answer. I'm hoping to hear that everybody has seen a power expression before in their life. Let's first look at the anatomy of exponents or a power expression, and next we are going to move to the physiology of exponents. I love to mix and match biology with mathematics. I love them both. Alright, so a power expression is something like x to the power y or 2 to the power 3. Now to get the terminology out of the way, this letter here, A, it is a symbol used for a number. And this number, it is called as base. This is the number that is being multiplied by itself. How many times? B number of times. So this B is the exponent. Sometimes it's also called as the power, even though technically speaking this entire expression, A exponent B, that is your power expression. But many times we also say it's A to the power B. I'm sure you have heard that before. So this exponent or the power, it is a symbol for a number. And that number, it is the number of times that this base, whatever number is at the base, it is multiplied by itself. So simply speaking, the power expression or the exponents, it's a shortcut for writing repeated multiplication. What I mean by that? Let's look at that on the next slide. A to the power B. All it means is that multiply A by itself B number of times. Now you may have had some numbers such as 2 to the power 7. What it means is that you multiply 2 by itself 7 times. So that's a lot of writing, right? And a lot of keeping track of how many numbers you have already written. So here you go. Do I have 7 here now? These are the pairs and I have 1 left. Yes, here you go. I've got 7 2's multiplying with each other. This is a lot of work, don't you think so? So instead of writing 2 times 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 2, I lost track of how many 2's I have already had. Instead of writing that, we simply write 2 to the power 7. Well, think for yourself. 2 to the power 7, it is still not a very big number. What if we have something like 19 to the power 19? Now just writing 19 to the power 19 completely. That is multiplying 19 by itself 19 times. That alone might hurt your hands and might make you run away from mathematics forever. We don't want that. So what we're doing is we are coming up with a shortcut method of writing repeated multiplication. So that's all this means. Power expression or the exponents. All it means is repeated multiplication. I hope that made sense. And I hope you already knew that. Alright, what's next? Now that we understand what is the power expression, next we're going to learn how to perform multiplication operation on power expressions. And let's learn that with the help of an example. Let's say you have 2 to the power 4 times 2 to the power 3. What that means is this. You have 2 multiplying itself 4 times, and that comes from over here, 2 to the power 4 times 2 multiplying itself 3 times, and this comes from over here 2 cubed. So here on the right hand side, how many 2's are multiplying each other? We have 1, 2, 3, 4, 5, 6, and 7. That means the right hand side is equal to 2 to the power 7. Now, is there an easier way to get this 2 to the power 7 other than multiplying out these 7 2's with each other? Sure is. On the left hand side here, we have 2 numbers multiplying each other. And each of these 2 numbers is a power expression. And each of these 2 power expressions has the same base 2. Now see for yourself that on the left hand side, the base, which is common for both the factors 2 to the power 4 and 2 to the power 3, if I write that down and add the 2 powers, which is 4 and 3. What do I get? I get 2 to the power 7 on the left hand side, just like 2 to the power 7 on the right hand side. You see that? Now this example here I showed only for two numbers, 2 to the power 4 and 2 to the power 3. But instead of just two numbers, just two power expressions, I could have any number of power expressions multiplying each other. The rule would remain the same. The pattern would remain the same. What that means is this. Here's what I mean. If instead of having just 2 to the power 4 times 2 to the power 3, I also have 2 to the power 2. Now on the right hand side, you can explicitly write them out. The repeated multiplication of 4 2's, then 3 2's, and then 2 2's. And then multiply out all the 2 2's. You will see that you have a total of 4 plus 3 plus 2. That is 9 2's multiplying on the right hand side, which can be written as 2 to the power 9. And how does this 2 to the power 9 come? By adding these exponents. So here is the deal. When you're multiplying power expressions, as long as the base is same, all you have to do is add up the exponents. So here, generalizing it, writing in terms of symbols. Why? Because in mathematics, especially in algebra, you're going to see a lot of symbols being used. So get used to it. So if you have a to the power m times a to the power n times a to the power l times a to the power whatever times a to the power p, a to the power q, and so on. When you multiply out all these a's at the end, what you're going to get is this. A to the power m plus n plus l. Keep on going, keep on adding these exponents till you get to p and plus q. That's all there is to the rule. And I hope that you understand how this rule comes about. So here we go. On the next slide, we're looking at product of powers, that is multiplication, when the base is same. That is, if you're multiplying two powers, a to the power m times a to the power n. Here the base is same in both the numbers, and that base is a. What do you get when you multiply them out? A to the power m plus n. And to bring this point home, let's look at one more example. If I have 5 to the power 25 times 5 to the power 15 times 5 to the power 10, then this could be simplified to 5 to the power 25 plus this 15 plus this 10. And that would be equal to 15 plus 10 here, that's 25. 25 plus 25 is 50. 5 to the power 50. Fairly simple, right? What if I had 5 to the power 25 times 10 to the power 10? Could I have written that as 5 plus 10 to the power 25 plus 10? Would this be right? Is this true? What do you think? We have some pretty big exponents involved here. Let's make the exponents a little small and work this out. Let's say instead of 25, I have 2. And instead of 10, let's make it 3. Okay. Now we know that on the left hand side, 5 to the power 2, that is equal to 25, times 10 to the power 3, that is equal to 1,000. So 25 times 1,000, that is equal to 25,000 on the left hand side. Let's make some room here. So here, 25,000 on the left hand side. On the right hand side, all we have to do is change this 25 to 2 and this 10 to 3. What do we get on the right hand side? 5 plus 10, that is equal to 15. 2 plus 3 is equal to 5. So 15 to the power 5, what is that equal to? Let's use a calculator for that. It is 759,375. Huge number. Let me write it down. 759,375. Obviously, 25,000 is not equal to 759,375. So what I did over here, this was totally illegal. You absolutely cannot do this. Why I showed this to you? Because this is one of the common mistakes I have seen many students make. I hope that you will not make this mistake. So how would you do it? So if you were to simplify this, 5 to the power 2 times 10 to the power 3, how could you do that? Here's what you would do. So we have 5 to the power 2 times 10 to the power 3. What I can do is, I will leave this 5 to the power 2 as it is. And this 10, in place of this 10, I'm going to write 2 times 5. Now 2 times 5, it is equal to this 10. And 10 is raised to the power 3. So I'm going to raise this parentheses to power 3. Now I can write this as 5 to the power 2 times 2 to the power 3. This 2 is to the power 3 times 5 to the power 3. Then the next thing I'm going to do is combine this 5 to the power 2 and 5 to the power 3. And that would give me 5 to the power 5 times 2 to the power 3. Is this correct? 5 to the power 5. That gives us 3,125 times 2 cubed is 8. Multiply them out and you get 25,000, just like we got it before. So alright, so we have taken care of the same base. Next thing that we're going to talk about is the same exponent. And I just showed that to you over here. 2 to the power 3 times 5 to the power 3. Where did this come from? This comes from here, 2 times 5 raised to the power 3. So I worked it out this way. On the next slide, we are working it out backwards. How? We had 2 times 5 to the power 3. I wrote that as 2 to the power 3 times 5 to the power 3. Over here, let's say A is 2, M is 3, times B is 5, M is 3. We are going from here to over here. Even though on the last slide, I went this way. See, depending on the problem, you got to pick which way you will go. The rule is this. Whenever you are multiplying two or more power expressions, where the bases may be different, but the powers are same, the exponents are same, then all you have to do is multiply out those bases together and raise that product of those bases to that common power. What I mean by that is this here. A to the power m times b to the power m. A and b in general, these are two different numbers that are raised to the same power m. And this is equal to product of the two bases a and b, and raise this product to the same power. That is on the left hand side. Now what? What if you have more than two power expressions multiplying each other where the powers, the exponents are same? Meaning, what if you have a to the power m times b to the power m times c to the power m, and why stop? Keep going till you hit times z to the power m. How can you simplify it? Well, you can write this as product of A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. I know, I love to sing that song every time I get a chance. So here, inside the parentheses, we have A times B times C times so on till you get to Z and raise this entire product to power M. And by the way, I hope that you know that whenever we are using symbols, we do not have to write the multiplication symbol explicitly. When I write this as A, B, C, going up to Z, it means that all of these letters, A, B, C, going till Z, they are multiplying each other. You do not have to explicitly write the multiplication symbol. And this is now raised to the power m. And for this one here, for the same base, if we had a to the power a times a to the power b times a to the power c, and so on till you get to a to the power z. Here I'm keeping the base same. I'm changing the exponents. Then the answer would be a to the power a plus b plus c plus d plus e till you get to z. I hope that this is making sense. If there's anything about this that is not making sense, please ask me in the comments section and I'm going to do my best to get back to you. After having a discussion of how to multiply power expressions, the next logical stop is how to divide power expressions. In other words, how do we get the quotient of power expressions? Just like we started the discussion of product of powers with the help of example, let's also understand the quotient of powers with the help of an example. Let's say you have two numbers, 2 to the power 6 and 2 to the power 3. Let's divide them. That is, let's find the quotient of 2 to the power 6 and 2 to the power 3. Now, the numerator, we could write it out as product of 6 2's. Here you go. We got 6 2's at the top. And at the bottom, where we have 2 to the power 3, we will write it as product of 3 2's. How do we simplify it? Well, easy. Let's say this 2 at the bottom cancels out this 2 at the top. Likewise, this 2 at the bottom cancels out this 2 at the top. And this 2 at the bottom cancels out this 2 at the top. How many 2's do we have left? We have 3 2's left at the top. That is, we have 2 to the power 3. That is left at the top. Now, is there a simple way to evaluate what is 2 to the power 6 over 2 to the power 3 without having to go through all this work? Sure is. Now watch this. As long as the base is same for the quotient, so the base is 2 here, all you have to do is write the base and raise it to the power, which is going to be the difference of the two powers. The power at the top minus the power at the bottom. That's all you have to do. For instance, let's take another example. Let's say you have 5 to the power 3 divided by 5 to the power 5. How can we simplify it? We can write this as 5 to the power 3 minus 5. This is equal to 5 to the power minus 2, which, as you can see, 5 to the power 3 over 5 to the power 5. It can be written as 5 to the power 3 over 5 to the power 2 times 5 to the power 3. How so? This 5 to the power 5 can be written as 5 to the power 2 times 5 to the power 3, using the product rule when the base is same. Now this 5 to the power 3 at the top cancels out this 5 to the power 3 at the bottom. And you're left with 1 over 5 to the power 2, which can be written as 5 to the power minus 2. Simple. Now pay attention. Here when we're finding the quotient, the base is same. Alright. So going back to the previous slide. So here you go. Whenever you're finding the quotient of two powers where the base is same, the answer is going to be the common base raised to the power the difference of the two powers, where it's going to be the power of the numerator minus the power of the denominator. Simple. Now what if The base of the two powers is not same, but the exponent is same. In that case, what do? Let's take an example again. Let's say you have 3 to the power 2 divided by 2 to the power 2. The numerator can be written as 3 times 3 and the denominator can be written as 2 times 2. This is equal to 9 divided by 4, which can be written as 3 over 2 times 3 over 2. 3 squared divided by 2 squared. It is equal to 3 over 2 squared, which means this a to the power m divided by b to the power m. It can be written as a over b to the power m. As you can see, the product and the quotient rules for the exponents, it can be categorized into two kinds. First, when the base is same. Second, when the exponent is same. Same base, same exponent. These are the two possible categories. Now, when we talk about the product here, base is same. That means we have A, however many A's. But the power, it is in general different. It can be same. Sure, I could have a to the power m times a to the power m times a to the power m again and a to the power m. I could have that. The answer here, the simplification here would be a to the power m plus m, however many m's are here. Let's say you had 10 m's here. We had 10 of these numbers here that are being multiplied. Then your answer would be a to the power 10m. Make sense? But let's say we had different exponents. We do not have same exponents. Maybe some of the exponents are same, some of the exponents are different. Let's say we have a number 2 to the power 2 times 2 to the power 3 times another 2 to the power 2 times 2 to the power 2 times 2 to the power 4. What do we get? We get 2 to the power 2 plus 3 is 5, 5 plus 2 is 7, 7 plus 2 is 9, and 9 plus 4 is 13. This is your answer. So this is how the product of powers works when the base is same. All you have to do is write down that common base and raise it to the power, the sum of all the exponents. That's it. So this is when we have the same base. Next, what happens when we have the same exponent? So here what you're going to do is, let's change the color. Let's say you have different bases, A, B, C, D. But they're all to the power m. Then all you do is multiply all these bases together and raise it all to the same common power m. Simple. Let's look at an example or two. Let's get rid of this from here now. You have 2 to the power 3 times 5 to the power 3 times 4 to the power 3 times another 2 to the power 3. How would you simplify it? You would do 2 times 5 times 4 times 2 to the power 3. You could simplify it further. This 2 times this 2. That is 2 squared times 5 times 4 to the power 3. Now this 2 squared, this is 4. So you can say that this 4 times this 4. This is equal to 4 squared times 5 to the power 3. Now if you want, 4 squared is 16 And 16 times 5, that is equal to 80. 80 cubed. All right, let's work this way. 80 cubed, what's that going to give you? Do you really want to find out? Sure, why not? 80 cubed is 512,000. Are you surprised that 80 is such a small number? I mean, relatively speaking, and its cube, that's giving you like 500,000. But think, if instead of this 80, you had 100. Now 100 is only 20% bigger than 80. But 100 cubed is 1,000,000. While 80 cubed is 500,000. So see the power of power? No pun intended. So this was a discussion of product. Let's now talk a little bit about quotient. Let me put another slide in here. So we're discussing quotient of powers. So first we talk about same base. Then we talk about same exponent. Alright, so same base, a to the power m divided by a to the power n. What does this give you? A to the power m minus n. Okay? Same exponent. Let's say a to the power l divided by b to the power l. Exponent is same, but the base is different. This can be written as the quotient of a over b, and this quotient is going to be raised to the power L. Now, I want to show you something very, very important here, and that is, let's say you have a to the power m, and we are going to divide it by a to the power m. Then using this rule over here, what do we get? A to the power m minus m. What does that give you? A to the power 0. So we show that a to the power m divided by a to the power m, that is equal to a to the power 0. But now, any number divided by itself, the quotient is equal to 1. So that means here, this a to the power m divided by a to the power m, this is also equal to what? 1. And we just showed that a to the power m over a to the power m is also equal to a to the power 0. So can we say that a to the power 0 is equal to 1? Now this is one of the things I had shown you earlier in the discussion of this lecture. And I told you that I will show you how a to the power 0 is equal to 1 using a different method as well. And this is what it was. Anytime you divide a number by itself, that is a to the power m divided by a to the power m, that is equal to 1. And by using this rule of the quotient of powers, we can also show that that is equal to a to the power 0, where a is any number. So a to the power 0, that is any number to the power 0, is always equal to 1. All right. So here on this slide, we have a snapshot of all the rules that we have discussed so far. Moving on. Power of a power. Sure. What does it mean? It means a to the power m is raised to power n. What does it mean? Now we know that power means repeated multiplication. Now whatever is here inside the parentheses, it could be anything. Call it a heart. We raise this heart to power n. That means multiply heart by itself how many times? N number of times. Keep on going until you have n hearts multiplying each other, right? But here instead of heart we have a to the power m. So what that means is multiply a to the power m by itself n number of times. So if n is equal to 10, we'll have 10 of these a to the power m's multiplying each other. Correct? Correct. So here you go. Using the rules of the product of powers where the base is same, we know that it can be written as a to the power m plus m plus m, however many number of these powers are being multiplied. Alright? Now you know that. If you have 2 plus 2 plus 2 plus 2, that means you have 4 2's multiplying each other. That is 4 times 2. So what we're saying here is that we have n number of m's multiplying each other. So we have m plus m plus m, keep on going. We have n of these, n as in Nancy. So this is going to be equal to this sum. This will be equal to n times m. Or you can say m times n. This is how this power mn comes. Cool? Cool. Moving on. So note, so when you raise a power to another power, the exponents multiply. For example, 2 to the power 2, that entire thing is raised to the power 3. What does it give you? That gives you 2 to the power 2 times 3 equals 2 to the power 6. And you could actually explicitly work it out and see for yourself that this is true. How? I'll show you for this one example. 2 to the power 2, and this whole thing is raised to the power 3. So this is 2 to the power 2 times 2 to the power 2 times 2 to the power 2. So each of these 2 to the power 2's, they can be further written as 2 times 2. This times. Now let's move on to this 2 squared. 2 times 2 times this 2 squared, 2 times 2. So here you go. How many 2's are multiplying each other? 6 2's. So this is equal to 2 to the power 6, which is same as saying 2 to the power 2 times 3. And this 2 and this 3, they are these exponents over here. Made sense? I hope so. Moving on to the next slide. Aha! Power of a reciprocal. Now here we have 1 over a, and we are raising it to power n. What happens? Let's look at example. We have 1 divided by 2. Why 2? Let's stick with small numbers. They're easy to work with. But don't underestimate the power of these small numbers. Again, no pun intended. 1 over 2 raised to the power 3. Just by definition, this is equal to 1 over 2 times 1 over 2 times 1 over 2. Now this can be written as 1 over 8. This can be written as 1 divided by 2 to the power 3. Get it? Okay. So basically what I have shown you with an example is this. This power n of this fraction, this power is going to go become the power of the numerator and the power of the denominator. That is, this is going to become 1 to the power n divided by a to the power n. But 1 to the power n, that is equal to simply 1. So what we get is 1 divided by a to the power n. Here you go. And here you go. Simple enough. Applying a power to a reciprocal applies the exponent directly to the denominator because 1 to any power remains 1. Want to look at some more examples? Why not? 1 over 5 cubed. This is equal to 1 over 5 cubed. 1 over 125. All right. Negative base. Well, we know that real numbers can be positive or negative. Now, whenever you have a negative base, then whenever you raise it to power n, if the exponent n, it is an even number, then you get a to the power n. Why? Well, you know that. Two negatives, when they multiply each other, you get positive, right? So if n is even, that means minus a. It is multiplying itself even number of times. So even number of times that these minuses, they are going to multiply to give you positive answer. Let's look at an example and let's keep the example simple. Let's say you have minus 1, that's your base. You're going to raise it to the power 2. What do you get? Minus 1 times minus 1. 2 minuses give you 1, right? What if you had, instead of this 2, you had 4? What will happen? Multiply it with 2 more minus 1s. Answer is still 1. So anytime you raise a negative number to an even exponent, your answer is going to be a positive number here. All right. Now that we have looked at what happens when the exponent is even, next logical thing to look at is what happens when the exponent is odd. And I bet you can guess that. So if n is odd, for example, let's keep the same numbers, minus 1. To the power an odd number, what should I take? How about 1? It's an odd exponent. Answer will be minus 1. If I take minus 1 to the power 3, answer will be minus 1. You don't like minus 1, it's too easy? Make it minus 2. Minus 2 to the power 1, it is minus 2. Minus 2 to the power 3, that is going to be minus 8. It can be written as minus 2 inside parentheses and cube this 2. And that's all we're saying here, that if you have minus a to the power n, if n is an even number, then you get a to the power n. And if n is an odd number, then this minus comes out and you get a to the power n. That is, if you have minus 5 to the power 5, this is equal to minus times 5 to the power 5. This can actually be written as minus 1 times 5 to the power 5. All I'm trying to show you here is that this negative sign is not a part of this 5 anymore. This is multiplying 5 to the power 5. And 5 to the power 5, we did that a while ago and it was equal to minus 3125 here. While if I had minus 5 to the power 4, then that would have been 25 to the power 2, which is 625. Here you go. It would be a positive answer. Alrighty, moving on. Here, just a note over here that division by 0 is not defined. I think I should have put this note where I had defined negative exponent, not negative basis. So this is kind of a little out of place, but it's very important nonetheless. So I do not want to ignore it. Anytime you're talking about negative exponents, that means 1 divided by anything, any number, then this number, the space in the denominator, it cannot be a 0. Why? Because 1 over 0, it is not defined. Any number divided by 0 is not defined. That's all. Alright, so here the laws of exponents. Once again, these are all the laws of exponents that we have discussed in this lecture so far. Hopefully you understand them. Hopefully you do not need to refer back to them because you understand them. But for just in case, take a screenshot of this. Why? Because I'm about to present you with the post-test. In the post-test, you will be given a bunch of problems, and I want you to solve those problems and write down those answers. After I show you all the problems, I'm going to go over the answers. Now mind it, I said I'm going to go over the answers, not the solutions. Why? Because if I included the solutions in this lecture is going to get extremely long. So if you want to go over the solutions of the questions, the problems that I'm about to present to you, then go to the next lecture in the series where I will solve every single one of those problems. For now, grab your notebook and get ready. I'm about to present you with your first set of questions. And just like before, I will stop at each slide for about 5 to 10 seconds. Just enough time for you to either pause the video so you could look at those problems as you're solving them, or take a screenshot and you can look at the screenshot and solve those problems, however you like to do. And here I am back. So part A, evaluate power. So here I'm asking you to write down the number that you're going to get when you multiply out these powers. 3. Like 4. I said, I'm going to stop on each of these slides 6, with problems 7, for about 10 seconds. Your 9, timer begins 10. Now. Moving 1, on to the next slide. 2. Here, part B, product of powers. I want you to simplify these. That means write the answer as a single power. Okay? Your timer begins now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Moving on to the next slide. Part C, quotient of powers. Simplify. Once again, you have to write your answer as a single power. Your timer begins now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Moving on to the next slide. Part D, power of a power. Now notice, here it says simplify, not evaluate. Evaluate will be something like if you had, let's say you have 2 to the power 2 to the power 2. If you're asked to evaluate it, then your answer would be 16. If you're asked to simplify it, then your answer would be 2 to the power 4. See the difference? Here you are asked to simplify it. That means this answer. Okay? Alright, your timer begins now. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Moving on to the next slide. Simplify completely. This is mixed exponent rules, so pretty much any of the rules of exponents is a game now. Your timer begins now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Moving on to the next slide. Yep, like I said, there are a whole bunch of problems for you to practice. But don't worry, you're getting close to the finish line. Here, simplify or evaluate. Okay, your timer begins now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're about to move on to the next slide, and that is the last slide of problems. Different looking bases. Some of these problems might be a bit tricky. I want to hold the bar high for you guys. Alright, your timer begins now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here, you guys were given total of 28 problems on this post-test. I will now go over the answers for these 28 problems. So get your answers ready to check them. Number 1, the answer is 81. Number 2, the answer is 1,000. Number 3, the answer is 1. Number 4, the answer is 16. Number 5, the answer is -8. Number 6, the answer is x to the power 7. Number 7, the answer is 5 to the power 5. Number 8, answer is a to the power 3, a cubed. Number 9, the answer is m to the power 2, m squared. Moving on. Number 10, answer is x to the power 4. Number 11, a to the power -2. Number 12, 7 to the power -5. Number 13, 1. Number 14, 6 to the power 6. Number 15, b to the power -10. Number 16, 2 to the power 24. Number 17, x to the power 4. Number 18, m to the power 9. Number 19, 2 to the power 5. Next slide. 21, 6 to the power 7. 22, 48 to the power 3. 23, 4 to the power 8. 24, 12 to the power 3. Number 25, 2 to the power 7. Number 26, 3 to the power 8. Number 27, 2 to the power 5. Number 28, 8 to the power 2. Hopefully you scored 100% and you feel confident that you can solve any problem on exponents. But if for whatever reason you did not do so well on your post-test, then you can find the solutions of this test, this post-test, in the next lecture in this playlist. I hope to see you again very soon next time, either in the next lecture in this playlist, which is the solution for this post-test, or in the lecture after that, which is going to be a test, a pre-test on numbers, the number system. And that pre-test is going to be a fairly short pre-test, and that next topic of the number system is going to be a fairly short topic, but important nonetheless. I hope that you all had as much fun learning about exponents as I had about teaching them. I'll see you again next time very soon. Until then, have a good one.